Hi, everyone. My name is Yichai. I'm your computer lab TA, and this is the pre-recorded video for our first computer lab. So I have uploaded the presentation file on Canvas. So if you click announcements, and you will see I have one post here showing Computer Lab #1 presentation and pre-recorded video. So if you click into it, you can see the presentation file showing in the bottom. Yes. So if you click it, then you can open it. And I'm going to quickly go through what we are going to cover during the computer lab. And I would suggest you guys to quickly review it and reserve your questions, and we can answer it during the computer lab. Here. Okay, so this is the presentation file. So in our first computer lab, I'm going to demonstrate how are you going to simulate 1D quantum wells and simulate the mini-band structures inside the quantum well in indium gallium nitride quantum well sandwiched by gallium nitride barriers. Yep. So this is the outline. So what is TCAD, and second one I want to explain is getting to know Crosslight, what is its capability, and third one is the lab activity, which is to simulate 1D quantum well. So TCAD stands for Technology Computer Aided Design, or stands for TCAD. It's a modeling software designed for device level simulations. So typically, our device is modeled in a continuous space, but modeling in continuous space is impossible in computers. So we need to discretize the device into like a finite element. So this is typically called a finite element analysis. Yeah. And some programs use other methods like Monte Carlo simulation or quantum transport like NEGF. They typically use different methods for simulation, but here we are solving just quantum corrected drift diffusion models. So how it works. So finite element analysis is to break a large problem into a large number of smaller problems. So for example, partial differential equation is typically solved in a continuous space, but we can approximate this partial differential equation into a set of additions, subtractions, multiplication, and division. So in order to do that, we need to generate meshes, which is to discretize the continuous space into finite space. Yeah. So the second part would be the mesh generation, and then we can solve the partial differential equations based on the mesh we generate. So why are we using TCAD simulation? There are a lot of reasons, but basically we are trying to reduce the cost to design a device or to study a device, because typically fabricating a device in clean room will take more than 4 months from design to measurement. And also the knowledge. So typically we have a lot of complicated physics behind this operation or behind device operation. And we want to study what is its qualitative dependence of one parameter on the device performance. And we need to use simulation to study that kind of effects, like electron blocking layer or current spreading layers. Yeah, so this is the Crosslight Apsis is one of the simulation software. There are a lot of simulation software out there that can simulate light emitting diode or solar cell. For example, Centaurus TCAD by Synopsys company also can do the similar things, and we still have other software like Silicon. It's also a good simulation software to simulate light emitting diodes. But here we are covering the Crosslight EPSIS, and the user interface is actually really good compared to other softwares based on my personal experience. So you can access to this software by clicking Start or Program, and you can find EPSIS 2021, and you click on this executable program called simuepsis.exe. Yep, and so this is like an overview of what is going on in this window. So on the left-hand side, you can see the input files, output files. On the right-hand side, you can see you have text editors. In the bottom, you can see the logs and the messages. So most of the time, you will use text editor to modify the codes. And then when you run or execute your program, you will see the logs and the messages to see if the convergence is stable or if the convergence has been reached or not. Yeah. So it's very important that Crosslight has a lot of functions, and we cannot cover all of them in the lectures. So most of the time, if you want to make your own project, some innovation project requires you to really go deep and study by looking at their manual. You will find out there are a lot of functions you can play with, and that can be part of your final project. So you can access to the Crosslight manual by clicking help and the general manual, or you can just directly locate to the folder where it's located. And I think this is very important for your self-studying. Yeah, and okay, so this is more like a computer lab structure in this semester. We changed a lot of things from one semester to another. So in this semester, we're going to have a pre-recorded video uploaded 1 week prior to each lab on Canvas. And you are expected to review it and bring all of your questions to the lab. So in the lab, you are also expected to join Zoom meeting while using Crosslight EPSIS. The reason behind it is because we typically will help students to debug their codes, and because of COVID, so typically we want to maintain a good social distance between students and TAs, or from one student to another. So typically we would like you to share your screen if you have any questions, so that I can broadcast your screen on the screen board and explain your questions so that everyone can learn together. Yep. And typically we have 3 or 4 computer labs, 3 to 4 lectures that we want to cover for the entire semesters. So some of the labs is relatively easy, so we will use like 2 lecture periods to complete the lab. But some of the lecture might be a little bit difficult, so we might use like 4 computer labs or 4 lecture periods to cover the topic. Yeah, and we also offer 3 bonus lectures. We will record it and provide source codes on Canvas, and you can access to it if you are interested in like a micro LED simulation, cubic LED simulation, and the multi-junction solar cell simulations. Yeah, and I think the techniques demonstrated in those 3 bonus contents are very important if you want to come up with some innovative final projects. And yeah, so when they are announced, I will let you guys know. And one important takeaway here is that our next quiz is on February 21st, Monday, in Computer Lab. So this quiz will basically cover the lecture that I want to cover, cover the first lecture. which is 1D quantum well simulation. Yes. So Crosslight file has a lot of file types. For example, .layer file is the file that defines your layer's geometry and or layer structure. And GEO file describes the full detail of device geometry and the initial mesh allocation. You don't really need to prepare this file because once you prepare a layer file, the program will generate GEO file and the material doping these files for you. But you just need to know that what it stands for. So GEO stands for the description of full device geometry and the initial mesh allocation, and material file contains material information that will be used for the solution file. I will talk about solution file later. And doping file contains the doping information for the solution file. So these files are more like intermediate file for Crosslight to process. Yeah. Plot file, actually we don't really need to use this one, but it can be used to plot the mesh file generated by .geo file. Yeah. And solution file. So this is the main input that we will work with in the second lecture. This is the main input file that defines the material properties and control the bias and other conditions of main equation solver. So we can apply different models, different set of equations that we want to solve in this file. A gain file is like a simplified version of solution file. So in this lecture, we are going to use gain file to tell the program what kind of model we want to solve. Yeah, we want to apply. So this is the auxiliary file to preview optical gain spectrum, spontaneous emission spectrum, quantum well subbands, and other critical physical properties. And PLT file is used for plot data from simulations in a .out file. So out is like an output file, and it shows like a structural data for you to preview. And RT gain file is very similar to gain file, but we won't cover it in this semester. Yeah. Okay, the first step here is to generate your first project. So because we want to build a Indian gallium nitride quantum well sandwiched by gallium nitride barrier, and we want to study what is the subband formation. So first, we need to start a new project. So you click like File, New Project, and select the project path. But be careful, don't put any space within. And there are a lot of students in the previous few semesters, they just put a space within and cannot compile their project. So without space, please. And don't save it under the shared folders, please. But don't just save it on the desktop. Please save it under like a D drive or C drive, but not desktop, because your desktop is just under the shared folder. Yeah. And you can set your project name to like a 1D quantum well, or you can set whatever you want and click next. We want to add the .layer and the .gain files because for this particular simulation, we only need to define our geometry and like a simplified solution file, which is gain file. Yeah. Yes, and you can open a 1D quantum well .layer file on the left-hand side of the input file. Click Open Layer Builder. So this layer builder is a GUI for device generation. Yeah, and our first step is to add a column. So we added like a first layer of device. And to construct a device, first we need to add a column and put layers on top of it. So this is the way how it is labeled if you put the first column, it's called column 1, layer 1. If you put second column, then it would be called like column 2 and column 3 and so on. If you put another layer on top of it, then it's layer 2. So if you, for example, if you want to access this block, it's called column 2 and the layer 2. Yeah, and this is how it works. And then our first layer has a width of 5 nanometer and height of 4 nanometer. So this would be like a Galilean barrier. Yeah, so in the material library, we select gallium nitride and model is bulk because quantum barrier is like a bulk structure. So we select our material and we select our model, very simple. And next, we define the mesh size. So in the column mesh, we are going to discretize this 5 nanometer with 3 data points, 3 meshes. Yeah, and the minimum mesh you can have is 3. So here we want to study the quantum effect in the vertical direction, but on the horizontal direction. So we can have like a small mesh size. We can have we could have small number of mesh in the horizontal direction, and large number of mesh in the vertical direction. Because the more mesh you have, the more accurate the result is. But then you increase your computational time. And so you need to find a good balance. And once I define the mesh, the number of mesh in the column region, then next we define the number of meshes in the vertical direction, which is it's called layer mesh. So here we set the mesh number to 6. What this stands for is that within this 4 nanometer of 4 nanometer high, we discretize this continuous space into 6 data grids. Yeah. And then we click OK. We generate our first gallium nitride layer. And we can recenter it by clicking zoom to fit on top of the program, and then it can be recentered. And you can select the layer by just clicking it, and the color will change into dark gray. Yeah, and you can, once you select it, you click add a layer, and the layer will be added on top of it. And the second layer would be Indian gallium nitride, which is quantum well. So here I provide the information for this layer particularly. So in Indian gallium nitride, the width is 5 nanometer and height is 3 nanometer. The reason why we put width of 5 nanometer is because our first layer gallium nitride has a width of 5 nanometer as well. So here we put the same width, but the height is 3 nanometer, meaning that we have 3 nanometer quantum well. And we similarly use the same mesh number for column mesh. We use the same number for layer mesh. But you need to know that because the height is different between Indian gallium nitride quantum well and the gallium nitride barrier. Here we have 3 nanometer. This 3 nanometer will be discretized by 6 meshes. So compared to gallium nitride, which has a height of 4 nanometer with 6 mesh number, Indian gallium nitride has finer mesh. Yeah, so each mesh is about like 0.5 nanometer. Yep. And we select a material to Indian gallium nitride. We want to put like an Indian mole fraction. So we click show load macro parameter. And on the right hand side, you need to tell the program that this is like a quantum well, so that the program will apply, will solve Schrodinger equation in this region. Yeah. So if we click load the macro parameter, then we can set Indian mole fraction. So you can put like 0.45 in this block, and you click OK, then your second layer is done. And because our first gallium nitride quantum barrier is the same as the other quantum barrier. So we can simply select gallium nitride layer. So you can see it's dark gray, and click copy layer, and select indium gallium nitride. Oh, sorry. Select indium gallium nitride second layer and click paste layer on top of the selected layer, so that you can generate another gallium nitride layer with the same setting. Yeah. Then this is the complete structure. So in the first layer, we have bulk macro gallium nitride with a thickness of 4 nanometer. We have the second layer, which is indium gallium nitride with indium mole fraction of 0.45. And this layer has a thickness of 3 nanometer. And we are applying quantum well model to the second layer. And on top of it is the same gallium nitride quantum barrier as the first layer. Yeah. Then once you leave the layer builder, you will see this layer builder is going to help you generate dot layer file in a command line. Yeah, and here I would like to highlight that if you use like a double end symbol at the end of a line, which means that it will continue. The second line is it will continue to the second line. Yeah, on the second line. Okay. And next step, once you have your dot layer file, then you generate your geometry file by right click on the layer file on the left hand side, and you click process this dot layer file to generate dot geometry file. And once you have the geometry file, you need to generate mesh file. So you just need to right click the dot geometry file and generate mesh, or you can click generate all, and they will yield the same results. Yeah, and next we are going to tell program what kind of project we want to solve. So in the .gain file, you first tell the program that I want to plot data into the result into .pdf file, and we want to include the file, the material parameters, material file in this .gain file. So you need to replace this project name by 1DQW or the project name that you set by yourself. And we set active region quantum print equals to 2. What that means is that you tell the program to print or to output the quantum well information like wave functions. So this line is needed. And second, you add this self-consistent. This syntax simply tells the program to solve a quantum corrected model, quantum corrected drifted diffusion model self-consistently. And then you add one line of band distance, ignore V band equals to yes. What that means is that in the output file, we will only show the conduction band structure, but not the valence band structure. So if you want to study the conduction band and the valence band at the same time, you need to put this yes into no. You need to replace this yes with no. Yeah. So there are a lot of built-in plotting format for this line: plot data, plot device equal to PDF. You can choose like post the script instead of PDF. Then the program, the output file will generate like .ps file, and you can open it using like the new plot to open it. But personally, I prefer PDF file because you can generate, you can open it with just Adobe DC. Yeah. And once you have defined your .gain file, you right click on it, you select gain preview, meaning that you tell the program to execute these codes, and it will generate the results. And if you want to see your result, you will find out a output file generated named output.tdf. You open it. The first figure you can see is the conduction band structures. So this conduction band is gallium nitride with 3 nanometer Indian gallium nitride and 4 nanometer gallium nitride. And this is the wave function of the first state, electronic state. This is the wave function of the second electronic state. I guess this wave function is the square of the wave function. This is not the exact solution of the wave function itself. I think this is just the square wave function. Yeah. So this would be like a probability density of electron. Yes. Then you can show the electron concentration as a function of position. And this electron concentration can be contributed from the first subband, second subband, and the bulk can also be shown. So you can see that for this Fermi level, this blue line is quasi-Fermi level for electron. For this blue line position, because the first state is very close to this quasi-Fermi level for electrons, so most electrons are going to occupy this state. But if I move this quasi-Fermi level above to this position, then you can see that the second band will start to be occupied by electrons. But because the second band is about more than like 10 or 100 kT away from this quasi-Fermi level for electrons. So you can see that in this plot, you can see this green line, which is the electron concentration with the energy in the second subband. It's very small, so you cannot see its contribution. Yeah, and finally, in the folder, you can see 2 different files called QWS0000 and also .gain.msg located in the project directory. And you can locate to the numerical data, like how large this conduction band or how large this valence band is away from its reference level. For example, you can see on the right-hand side, there's a region showing like multiple quantum well subbands and quantum conduction band value equals to 1. You have 2 bands, right? 0.13 electron volt. The second band has an energy of 0.497 electron volt. What that means is that here you have the first state here is about 0.13 electron volt, and this is referenced to this the bottom of the quantum well. So that means this region is about 0.13 electron volt, and the energy difference between the conduction band and the bottom of potential is 0.497 electron volts. So if you want to calculate the energy difference between the first conduction band and the second conduction band, then you are going to subtract the second value by the first value. So the energy difference between the first and the second conduction band would be about like 0.36 electron volts. Okay, and next, in the valence band value index, this region, you are going to see the position of valence band. So the first column shows the number of valence bands. So you can see there are 6 valence bands inside the quantum well. And similarly, the second column shows the energy level reference to the top of valence band, the potential, the maximum potential. Yep. So you can see the first band is about 0.0265 electron volt away from the top of valence band potential. Yeah, and the third column is the energy difference from the conduction subband. So which conduction subband is referenced in this case, in this region? Then you can see here in the second line from conduction subband level 1. So this line, this value, 1.96 electron volts, this is the energy, or you can call it transition energy from the first, from the ground state of conduction band to the ground state valence band. Okay, and the overlap is the wave function overlap integral between electron and the hole, and they both locate in the ground state of their individual quantum well. Okay, yeah, so if we want to calculate like the transition energy from the ground valence band to the second stage in the conduction band, then you are going to use this value, because you can see here, this is the energy reference to the second conduction subband level. Yeah, so this 2.327 electron volts, this one is the energy difference between the second level in the conduction band and the ground state in the valence band. Yes. And I think that's for it. And I hope you enjoy Computer Lab, because then you will gain some experience in simulation and computational modeling. And yeah, that's it. Thank you.